All right, so here's a few news articles. The Trump has really decided to pick a fight with Fauci, and they're now openly announcing that they're doing this herd immunity thing, which makes no sense at all. And Fauci is very clear that it's nonsense because they imagine that there's some safe group of people that won't get sick from coronavirus, and that is apparently not true. And the number of people that have underlying health conditions that make them vulnerable is like 30%, and there's no way you can protect them. So anyway, that goes on. And this is interesting. The new PlayStation, apparently Sony is worried that people are doing mean things in voice chat on PlayStation, which I don't know anything about, but that might be true. So they're going, you cannot use the voice chat without agreeing to let them record it and send it to Sony, where they will review it to decide if you're being abusive and punish you. So this, I think, has been an ongoing privacy issue with all the voice-sensitive devices. I remember there were teddy bears you could get that your kids could talk to, and it turned out that all that sound was being sent to a server somewhere out of your control. And there's these Google and Amazon things that are listening all the time. You talk to, and it turns out that they're picking up data they shouldn't be picking up and sending it at times when they shouldn't be sending it. You know, just in general, all these voice-controlled things seem to be too careless about privacy. So I thought, I've been waiting for the October surprise like we all have, I think. This is how Trump usually wins. And again, and students have been asking me, are the Russians going to do something? And this is it, apparently. It's just a repeat of the same thing that they tried a couple of years ago, leading to the impeachment. The same thing, claiming that Hunter Biden exploited his father's position. Now they're claiming they found some laptop, which seems transparently fake. And this is just Russian disinformation being laundered through Rudy Giuliani again, when he's already been caught several times doing exactly the same thing. So it seems unlikely that it's going to work this time. And I should find where the chat is. Looks like there is no chat anyway, but all right. Now there's a chance I might see it if there were some. Anyway, so this surprised me. A C-SPAN person who was going to moderate the next presidential debate said something not even terribly scandalous to Scaramucci. He got some comment from Trump, and then he asked Scaramucci if he should respond to Trump. But then when people asked him, why are you saying this thing? He said he'd been hacked. And then he had to admit he hadn't been hacked. So they're firing him for that. All a little mysterious to me, but that's, anyway. This is the first time I've heard of someone being fired for lying and claiming they were hacked when they weren't hacked. It's an extremely common thing that people do stupid things on social networks and then try to claim they were been hacked. And, you know, I don't know how often you can prove they haven't been hacked. People do get hacked a lot on social networks, but I'm sure they lie about it a lot too. This I thought was very interesting. Microsoft has a huge amount of security problems, as we all know, and they're much more mature than most companies are trying to deal with it. And so they figured out that 2/3 of all bugs, 70% of all bugs are caused by memory corruption, which is why if you take the exploit development class here, it's almost all memory corruption attacks. And one cure is to switch to the language Rust. And I've taught CTFs with Rust and have shown to use it. Rust is very popular among programmers. It's very easy to write secure code, but it runs very slowly. So Microsoft has been trying to, one project that's underway at Microsoft is trying to write some important part of the operating system, like part of the kernel in Rust, so that it will be more safe from these bugs. But there's another alternative, and that is this thing, Cherry, which is to change the hardware to build a different kind of processor, which is intrinsically more designed to protect against memory corruption attacks. So that is an interesting idea, and we'll see what comes of this. I know Apple is moving to ARM, and maybe Microsoft will move to this Cherry thing. All these things are going to take years to develop, but they are trying to find a good solution, because C and all the languages derived from C are just too dangerous. The way they handle strings in memory just leads to an endless chain of corruption attacks, and they have these pointers all the time. It just turns out to be pretty easy to get memory corruption in C-derived languages. So I have to do something about it. I came across this today. James Carville, who is a well-known political pundit, he's wonderful. This made me feel a lot better. And this is how I felt. A lot of people are, my friends are sort of think I'm crazy because I'm less depressed lately. Because I think, this is what I feel like. I mean, we are coming out of the Trump era. I mean, it looks like Biden is going to win, and then we're going to be at a very exciting, positive time in America, like the New Deal under Roosevelt or the Civil Rights Movement, when the backlash against Trump with the progressives should really be very exciting. We should be able to make some big changes. So anyway, Carville's married. I don't know who he's married to. It's a good question. I just heard him on a couple of podcasts, and then I listened to his podcast, and I found this article. He seems to be a wonderful, progressive, patriotic fellow that I like hearing from, but I don't know anything about him beyond that. He also has an outrageous Southern accent. At first, I couldn't understand anything he said, but it makes it easy to tell when he's talking. He's got a more extreme accent than anybody else I listen to. Anyway, so I feel like I'm feeling a lot better. Of course, after I voted, I felt a lot better about the election, I think, because I'm no longer worried if somehow I'm out of the game. But anyway, so I highly recommend voting by mail, by the way. The lines at the ballot boxes and all that nonsense are ridiculous. So Twitter is now going to remove Holocaust denial posts. And Facebook did it first, so this is part of the very strange situation. One thing I heard today about this is maybe what we should do with social networks is force them to all be interoperable. I mean, I've noticed my friends are sort of drifting away. I have some friends that like Facebook and won't use anything else. I don't like Facebook, so I never see them. I like Twitter. There's people that hate Twitter and want to use email. And so social groups fragment into these groups of people that use one platform instead of another. And it would be nice if they were all interoperable, so anything you put on one of them could be easily picked up at the others. That's an interesting proposal, and I wouldn't mind seeing that, because we seem to be technologically separating into little islands for no very good reason. Anyway, we're down to the official topic here. Let me check the schedule. So we are here. Yeah, authenticated encryption. All right, and I do have a guest coming, not on a Thursday night, but on Tuesday, November 3rd, Election Day. So please tune into this if you like. This will be Caitlin talking about hacking things off Earth, which should be a lot of fun, and it's worth extra credit if you come to one of these talks. So look at authenticated encryption. All right, so we already talked about message authentication codes, where you have a message and you put a tag on it, like a hash, which now a hash by itself would just guarantee integrity, but an authentication code also includes a secret key, so it also protects authenticity. So you know whoever put that tag on there had the secret key, so you think you know who they are, as long as people aren't losing the secret key. And you know that the message has not been altered, because you can verify the tag. So this is the next step, where you want to not only have authenticity and integrity, but you want to have confidentiality. So you want to have an encrypted thing with a tag on it, so it's not only protected from third-party snooping by encryption, but it also has a message authentication code in it, so you know it hasn't been altered, and you know who the author was. So they'll talk about how this is done, and there are various standards to be used for it. So the simplest thing to do is just use a message authentication code, right? So there are 3 ways to do it. You could just encrypt your message using encryption routine, and then separately create a message authentication code and just send both of those things. That would do it. Or you could calculate the message authentication code and then add that to the message and encrypt the whole thing. Or you could encrypt it and then calculate the message authentication code on the encrypted message. And all those will accomplish the job. They just have some minor differences in security. The least secure system is this, because if you think about it, you've got 2 pieces of information here that came straight from the plain text. So if either one of these systems has a flaw, then it might leak the data out. So in particular, if your message authentication code has a flaw that makes it possible to do something about the plain text, then you might get some information. It might leak out some information about the plain text that would have been protected by the encryption. So in practice, this turns out to be okay for the commonly used ciphers, but in principle, it's not the most secure way to do it. And so that's what SSH uses. Each encrypted packet is followed by a tag, and it turns out it is secure in practice because the message authentication codes don't in fact leak any information out because of the ones they use. All right, then you got Mac-then-Encrypt, where you calculate the authentication code and then you encrypt the whole mess to make ciphertext. That of course means that the MAC is mixed into the plain text and is not separable in the output, so that's more secure. And that's what TLS uses. TLS up to 1.3 used that, then it switched to authentication ciphers, which we'll talk about more later. And this is considered the strongest system, encrypt and then MAC, because now you can't possibly create this MAC without knowing the encryption, and the MAC can't leak any information out because it's all protected by the encryption. So that is considered the strongest system. In principle, in practice, they all seem to be good enough using the algorithms that are currently popular. All right, and so then there are authenticated ciphers, which instead of just taking two separate systems and combining them, create a new system that is designed exactly to solve this problem. So you're going to have a key and a plain text message. You run it through this thing, and it's going to create a ciphertext message and a tag. And to decrypt it, you put in the ciphertext message and the tag and the key, and you decrypt it and make sure the tag matches the expected value, and then you say you found the plain text. It's all combined together so you can consider making a specialized algorithm. So what you want is the authentication should be as strong as a MAC, and the confidentiality should be so strong enough that nobody can get in without the key. That's the plan. All right. And this will prevent chosen ciphertext. There are attacks, for example, some of the ones against web, where you feed it plain text and it encrypts it for you, and you can examine the ciphertext. And this is protected from that because you would have to have the tags, or it would come out in a random, useless way because of the tags. At first I thought I understood this, but now I'm thinking about, sending ciphertext. Okay, chosen ciphertext, right. I can't choose a ciphertext and get it to decrypt it, because any ciphertext I construct without knowing the key will not be valid. It'll just be rejected and not decrypted. All right. So it'll prevent things where you're modifying ciphertext, like the padding oracle attack that we talked about before. If you mess with the ciphertext, you'll just create rejected stuff in the decryption process, because you will not be able to make the tag right, and it won't accept any ciphertext without a valid tag. All right, so here's a system, AEAD, authenticated encryption with associated data. This is another issue. You might have some data that does not need to be encrypted, but you do want it to be authenticated in the tag. For example, if you're sending network traffic, you want to have some network addresses in the packet, and you want that to be probably verified, but you can't encrypt it because that has to be plain text to guide the traffic. So this is a real use case that matters, where you have a key and you have plain text and you have associated data, and you want it to turn it into ciphertext, the associated data, not encrypted, and a tag that proves that all this stuff is authentic. So those things exist. And in fact, if you make one of these, then you could leave either the plain text empty or the associated text empty. If you leave the plain text empty, then it doesn't encrypt anything. It just gives you data with a tag. So that's essentially MAC, just a MAC. And if you leave the associated data empty, then it's authenticated encryption. So this is a sort of system that could be reduced to any of the others. All right. Now another issue, of course, back here, is that if I were to send another message with the same plain text and the same associated data, I'd get exactly the same output. And then I'd be able to observe that it was identical. And that's a weakness you might want to avoid. So you could add a nonce to every one that keeps changing, and then you wouldn't even have that issue. Then even an identical message would have a different tag. All right. So here's your criteria. The confidentiality should be as strong as a good cipher, and the authenticity should be as strong as a good MAC. And also, you should consider the case if the nonce is accidentally repeated. because that's one of the many things that went wrong with web. They had a 24-bit nonce that was, and what happens is, as we know now because of the birthday paradox, if you have 24 bits, there are 2 to the 24 possible values, but if you choose them at random, after 2 to the 12 guesses, you'll have a collision where 2 packets are sent with the same nonce. So even if you make some effort not to reuse nonces, it tends to be the case that after a while you do accidentally reuse a nonce. And so it should be considered how much damage that would really do. All right, another issue is, can you process multiple blocks parallel processing to make it easy? Remember from before, this is one of the things that's wrong about cipher block chaining. You cannot possibly encrypt the next block until you encrypt the block before it to get the output to use as the IV. So if you had a parallel processing computer, it wouldn't do you any good. Counter mode is parallelizable. The nonce is just counting up through some pattern, so you can do them all independently. All right. So you can have a 2-layer system or a 1-layer system. In a 2-layer system, you encrypt the plain text, then you calculate the tag, or you might combine this all into one operation. That might be simpler and faster. It just depends on the details. All right, and then there's streamable. This is, if you have a long input message, can you just process one block at a time so you don't have to put it all in memory at the same time? That would be nice. For example, we mentioned before, MD5 and SHA-1 are this way. You can put in one block of data and the next block of data. You only have to process one block at a time. That's a streamable operation. A non-streamable cipher has to have the entire message available all the way through. And that is a defect for long messages. It will have more RAM requirement. All right, so some of them only allow you have to put the associated data somewhere. In some of them, you put the associated data before the plain text and concatenate it, or you put it after, or you put it in the middle someplace. It would be nice if you could put it anywhere you want, but that might get complicated. We talked before about linked extension attacks coming from where you put these things. It may matter where you put it. AES-GCM has 2 algorithms, one for encryption and a separate one for decryption. A counter mode can use the same algorithm for both, so that might make it cheaper to make the hardware for devices and such. Anyway, the current standard is GCM, Galois counter mode. I think it's probably French, I'm probably pronouncing it wrong. But anyway, this is just a version of counter mode that uses these Galois numbers to create the numbers you add in. And that's considered very good. It's the most widely used cipher. It's the only one approved by the American government, National Institute of Standards, part of the NSA suite. So it's used in a lot of modern protocols that come from America, or are approved in America, like IPsec, SSH, and TLS. So you have, it's encrypt and then MAC. You take the nonce and you append to 1 and take the nonce and append to 2. Then you run that through AES with the key, and that creates blocks of random bits. And then you just XOR those bits with the plain text, which is the way counter mode always works. And then that creates the ciphertext. And down here, you use this polynomial multiplication with a hash key, and then XOR, and then this polynomial multiplication, and then an XOR to combine the blocks of output here to get one block for the tag. All right. That's the game of it, and this thing is considered quite good. Here's an explanation of what this polynomial multiplication thing is, which is sort of mind-boggling, and I don't plan to go through it in detail, but they do explain it in your book if you're interested in the math of it. So this turns out to be bad if the nonce is used twice. If it's used twice, they can forge tags. And this did happen in the real world. They found some HTTPS servers with repeated nonces and somewhat nonces that were all zeros. So those are implementation defects. You know, it has a rule. You must have a new nonce. And since that's a little bit difficult, you know that sooner or later somebody's going to make a system and forget to do it. All right, they're both parallelizable, but the MAC isn't. It's streamable, however. So it's pretty good and quite popular and just the standard. Now there are some, as always, some other systems that are probably better in various ways. But the one that it became the standard is good enough, so nobody cares much about these others. Is generally something you hear almost every part of this class. So this one, Offset Codebook, is considered quite good, faster and simpler, but it was licensed. You weren't allowed to use it for free until 2013, so Galois counter mode became a standard. This has one layer with only one key. So you take each block of plain text and you encrypt it with a block cipher, and then you use an offset computed from the key and a nonce. You create these blocks of things. What kind of audio are you hearing, Jimmy? Is it just like traffic noise? It might be coming in through my window. Garbled sound. Let me see. I see. I found somebody was not on mute. Maybe that will help. Did it get better? Still there? Maybe it is my fans. Let me try turning off these fans, see what happens. Does that help? Okay, let me know if it works. Anyway, that helps. It was probably the fans. I was worried about all these fans. It's cooling off now, so I don't think I need them. Good, thank you for letting me know. Anyway, all right. So in the internal, it uses a series of XORs. Anyway, this is what you should be getting used to seeing here by now. It is nice, simple mathematical operations that can be fast and efficient. And this one also supported associated data. It's just doing a series of XORs of things to get the job done. And so it turns out to be better than Galois counter mode. Even if you repeat the nonce, it'll be okay. They won't be able to find the secret key. And it turns out to be pretty fast, parallelizable, and streamable. And there was a time when it was even faster than Galois counter mode, but that's not true anymore. Anyway, so it is an option that's out there in case we decide something's wrong with the others, but it did not become the standard because it was licensed. And here's another one, SIV. This is synthetic IV, which synthesizes an initialization value. It's considered secure even if you use the same nonce twice. And if you repeat, the attacker will only see a repeat there if the same complete plain text is repeated. Whereas other things like Galois counter mode, if you repeat the IV, if the first block of data repeats, they will see the first block of ciphertext repeat. So it is more secure in that regard. All right. Anyway, it's got an encryption function and a pseudo-random function and two keys. And so it calculates a tag as the pseudo-random function of a key and the nonce appended with the plaintext appended to it here. And the ciphertext is done with key 2. So it is not streamable, unfortunately. It must keep the whole plaintext in memory. So if you want to encrypt a big message, you need a lot of memory. So that's a defect. All right. And then there's permutation-based AEAD that does not use a key. It transforms input to output of the same size with a permutation function. And this turns out to be fast and secure and more resistant to nonce reuse. So you have an internal state, H0. You XOR with a key and a nonce, which only affects some of the bits here, because this is all put together, padded largely to make the size of the internal state. Then you run it through a permutation function that scrambles these bits together. Then you just keep XORing more blocks of plain text in and permuting again and again. So that gives you, then you can extract a tag from the bits of the internal state when it's all over. All right. So the ciphertext is the same length as the plain text. The internal state has to be larger, and some of those bits are used to make the tag. So the internal state must be kept secret. If that leaks out, then it ruins the security. And you keep having to pad data to make it long enough. Nonce reuse is only a small problem. It's streamable, but it's not parallelizable because you have to do one block before you do the next block. Oh, it's another alternative. Anyway, then there's things that can go wrong. So you have to have confidentiality and authenticity. So you want to make sure that for every plain text and every associated data, it must remain secure. So you consider duplicate values, making values all 0, so on, making values very long. Those are the edge cases that might typically give you trouble. So you must consider attackers who can collect many message tag pairs, like in WEP, where they can just collect millions of systems, and possibly some of them have repeated nonces. This thing, the lowest counter mode uses a hash, and it uses a hash key over and over. It calculates the nonce for one, and then it runs the hash function again to make the nonce for the next, and hash function again to make the nonce for next. And that'll be familiar with you now. That's what we did for Pollard's row. You keep hashing it and hashing the hash and hashing the hash. And as we know, that will form a loop at about the square root of n. So if you have n bits in the hash, so there's 2 to the n possible hashes, it's at the square root of that number, it will start repeating in a loop. So that means the nonces will not really be random. They will eventually fall in a loop and just keep repeating the same nonce values over and over. So there will be a time when you have repeated nonces here. And so if, for example, you were able to get a cycle that was very short, like a cycle of 5, then the nonce would be identical for the first block and the 6th block. And that would mean you could swap the first block and the 6th block, and they would still be valid. And that can turn out to be very serious. For example, here's one from another course. We had a similar system. If the one block here, you have a random number with a 1 here, and down here you have UID equals something, and this is processed by web application. If I'm able to swap this number, then I can change that UID. So this original thing has UID equals 0, but if I swap them, the UID will now be 1. So the fact that you can flip some data around so the data reaches out of order can turn out to be very serious. So in principle, that's a weakness. In practice, as usual, it's not much use because the hash function is not so short that the cycle is that short. And what's even worse is you can't find the cycle length. You'd have to know either the secret value H or the K secret value to find the cycle length. So, but you know, I suppose you could think of some attack where you gather millions and millions of ciphertexts, and then you try all possible key lengths and try mixing things around, and eventually you might be able to get away with something. So it's a small weakness. Anyway, so 128-bit tags are considered pretty good. You can run it with shorter tags, like 32 or 48, and of course at that point, it's much less secure. So anyway, here's a measurement. A 48-bit tag for a 4 gigabyte message has 1 chance in a million of a forgery succeeding, which is not very practical, but in fact, a lot of the attacks against modern encryption are this way. The whole series of attacks against versions of TLS, and they took billions of messages to get through. And you know, you'd like to have a system that is secure even against that level of attack. And this is part of what's wrong with voting systems. When people talk to me about how secure voting systems are, when I tested voting apps, I said, well, they look as secure as like normal commercial apps, but they have to really be much more secure because nation states that want to mess with your voting might really be willing to dedicate a supercomputer and analyze 1 billion messages in order to make a small change. You need a much more secure level of encryption for that use case. So here we are 141, chapter 8, I think that's right. Let me check my slides. Indeed, chapter 8, okay, good. Take a look at these. Set up a place to record them. All right. I'll give a few more seconds. guess that's it. All right, which one does not give confidentiality? All right. That's a Mac. Mac just puts a tag on it so you can tell if it's from the right sender and not altered. All right. Which one is the National Institute of Standards approved system? That's it. The lowest counter vote. That's the system that is approved. All right. Which one might leak information about the plain text? Encrypt-and-MAC. That's the one, because if one of these systems is weak, it might affect the other. And the one they talk about in your book, if the MAC is weak, it might leak out data that would compromise the encryption. All right, which system tags data for authenticity but not confidentiality? That's this one. You have this associated data, which is sent along and verified but not encrypted. All right. That might be someone's initials. I know who that is. And that's initials I know for sure. All right. Good. All right. So I'm going to stop the recording and probably